Hello everyone, I welcome you all for today's session on constants m and h of a multi-machine system. So we know the relation between the m and the h value, both will be called as the inertia constants of the machine. For the stability studies, we are assuming that the constant h is independent of the disturbance. That means it is not going to vary, so this will act as a pure constant. But if you coming to the m will have a term omega in the equation. So because of that, strictly it will not follow the term constant. So there are some chances of varying this m value because of the disturbances. So due to this reason, we have derived an equation between the m and h that already we know m is equal to g into h by 180f if the angle is in degrees, or you can say gh by pi into f. So this is the case where we have a single generator in the system. But practically, it is not a single machine and the single load connected, or the single machine or the infinite bus. So we will have the input side also multiple generators. So it may be the 2 generators, 3 generators or 4 generators. Several generators will be synchronized together so to take up a particular load. So how these multiple generators will be connected? Let us say we have several generators which have connected in synchronism. That means all these generators are synchronized together to take up a common load. So in this case, if you see, each generator will have its own specifications. Okay, so we cannot assure that whatever generators we are taking, all will have same rating and all will have the same inertia constant. So that is not possible. So to meet different types of the loading conditions, we will be connecting the generators with different ratings. That means this will have a different rating and G2 will have different rating. Similarly, the nth generator will have a different rating. So similarly, we will have different inertia constants for each generator as well as the EMF developed by the each generator also. That means we can say that this will be E1 at an angle del 1 and E2 at an angle del 2 and En at an angle del n. So this m term, it is with respect to the rotor dynamics. So that is, it is related to the rotor stability, or you can say the angle stability condition. So that means again it is related to the load angle del. To get the relation between the m and h, so our main concentration will be how this load angle will be for all these synchronous machines which are connected in parallel condition, or you can say in synchronization. Depending on the load angle of the several machines, multi-machine operation can be divided into two major types. So let us see what are those two types. Depends on the load angle value. We have two different types of operations. One is the coherent operation and another is the incoherent operation. So what is meant by the coherent operation means, whenever the load angles of all the machines which are interconnected or which are connected in parallel will be equal to each other, then that kind of operation will be called as a coherent operation of the synchronous machines. If the load angle of the each machine is different, so we have a different angles of each machine, so then you can say the system is running under incoherent operation. So in this session, we are going to see these two operations with respect to a two machine system. So for the analysis, maximum we will go for the two machine system in this subject. Therefore, we are going to see these two operations with respect to the two machine system itself. Let us consider a two machine system. So where the two synchronous generators, or you can say the alternators, are connected in parallel to supply a particular load. So let us say the G1 is having inertia constant M1 and the generator G2 is having inertia constant M2. the generator 1 will have the excitation EMF E1 at an angle del 1, where the generator E2 will have the excitation EMF E2 at an angle del 2. Since we have two generators, for each generator, that means if any disturbance occur, so we can write swing equation for each generator. That is, for the first generator G1, we have a swing equation that M1 into d square del 1 by dt square is equal to the shaft power of the generator 1 and the electrical power of generator 1. Similarly, second generator will have M2 into d square del 2 by dt square, that is equal to shaft power with respect to the second generator and the electrical power with respect to the second generator. So now we have two different equations with respect to the two different generators. So whenever you talk about the interconnected system, we need to bring one equivalent relation, so which refers to the equivalent circuit of the system. So let me say this will be called as M equivalent. What will be the M equivalent value? So how we can get this M equivalent from the given data? And we know that in the coherent operation, the load angle del 1 will be equal to the del 2. So we have a condition here, the load angle del 1 is equal to del 2. So now we have to derive an equation for the equivalent inertia constant M equivalent by using these two relations. So let us see how to do that. So we know these two equations. Now let us give the equation numbers, equation 1 and 2. So now by adding equation 1 and equation 2, so we will have M1 into d square del 1 by dt square plus M2 into d square del by dt square, that is equal to PS1 minus PE1 plus PS2 minus PE2. And we know here del 1 is equal to del 2. So I will say that del 1 is equal to del 2, which is equal to del. So if you consider that M1 plus M2 d square del by dt square, which is equal to, so let us separate the shaft powers and the electrical power. So PS1 plus PS2 minus PE1 plus PE2. So which I can further write this as shaft power equivalent value minus electrical power equivalent value is equal to, this can be represented as M equivalent into d square del by dt square. Now we got the M equivalent value. Suppose the given data is provided in terms of the H value. So they have given the inertia constant in megajoule per MVA or in seconds. So that is nothing but they have given the constant H. You know the H1 value, you know the H2 value. Then how can you find out the M equivalent value from the equations? So from this relation we know the M equivalent value is nothing but M1 plus M2. Let us take that equation. M equivalent is equal to M1 plus M2. But we know the inertia constant M is equal to GH by 180F, or you can say GH by pi F. So with respect to this equation, you can write M1 is equal to G1 H1 by pi F, or you can say G1 H1 by pi F. Similarly, you can write the inertia constant M2 is equal to G2 H2 by 180F, or you can say G2 H2 by pi F. So if we substitute these two equations here, then you can write the M equivalent value as G1 H1 by 180F plus G2 H2 by 180F if it is in degrees. So if it is in radians, you can replace this by G1 H1 by pi F plus G2 H2 by pi f. So this will be equal to pi f G1 H1 plus G2 H2. Suppose here also, since they have given in terms of the H1 and the H2 value, so the equivalent value also, if we want to represent in the H equivalent, we need to expand this M equivalent also. Therefore, you can write the M equivalent value as, again you know that M is equal to GH by 180 F or GH by pi F. So here you can say that M equivalent value is equal to G equivalent into H equivalent value. So similarly here G equivalent into H equivalent by pi f. So let us write that. I have written in terms of the radians here. So let me write this also in terms of radians. That is G equivalent into H equivalent divided by pi into F. So this and this will get cancelled. Finally, you can write the inertia constant H equivalent value is equal to G1 H1 plus G2 H2 divided by G equivalent. This is the base MVA of the generator and the G2 is the base MVA of the generator 2 and this is the common base MVA of the both. So you can say we will be selecting one common MVA for the entire system. So you can say that common MVA or you can say the base MVA of the system. So I hope it is clear. So the generator 1 is the first generator 1 machine rating, generator 2 machine rating and this is the base MVA of the system and H1 is the generator 1 inertia constant and H2 is the inertia constant of the generator 2. So finally we got two equations in a coherent operation, that means where the load angles of the interconnected machines are same. So then you can say that inertia constant M equivalent is equal to M1 plus M2. So H equivalent is equal to G1 H1 plus G2 H2 by G equivalent. So very important, when the synchronous generators are swinging together, so that means both the load angles are same. So that time the M equivalent value will be equal to M1 plus M2. So if they have asked you to find out in terms of the H, then we should remember this equation or you just substitute these values in this equation. So finally we could get this equation. So we no need to mug up this equation. By practice, if you remember just like that, it is well and good. But even if you are not able to remember also, you just remember this main equation, then just do substitution of these equations. So finally, we will get this. So now coming to the incoherent operation of a two machine system. Here also we are taking the same conditions, that is generator 1 is having inertia constant M1 and the rating of the generator is given as a G1 and the inertia constant in terms of megajoule per MVA as a H1 and it is having the induced EMF E1 at an angle del 1 and the machine 1 is supplying electrical power PE1. So now coming to the generator 2. So the generator 2 is having inertia constant M2 and the rating of the machine G2 and the inertia constant in megajoules as H2 and the induced EMF is E2. There is the excitation EMF of the generator 2 is E2 at an angle del 2. So now the power produced by the second generator, let us take PE2. So you can say that the two powers are in the opposite direction. This is the case where del 1 is not equal to the del 2. That means the two generators are not swinging together. Instead of using the term incoherent operation, they will ask you if the synchronous generators are not swinging together. So what will be the value of M equivalent? In this condition, how to find out the M equivalent? So as usual, you can write the swing equation for each machine as M1 into d square del 1 by dt square is equal to shaft power of the first generator and the electrical power of the first generator. Similarly, you can say M2 into d square del 2 by dt square is equal to PS2 minus PE2. So now let us try to get the m equivalent value from these two equations. I am going to multiply equation number 1 with constant m2 and equation number 2 with constant m1, and I am going to subtract equation number 2 from equation number 1. So this is what we are going to do now. So if you multiply equation number 1 with m2, we will get the constants m1, m2 into d square del 1 by dt square is equal to ps1 into m1 minus pe1 into m2. Sorry, this is m2. So let us multiply the second equation with constant m1. We will have m1 m2 into d square del 2 by dt square, that is equal to ps2 into m1 minus pe2 into m1. Let us take this as a equation number 3 and equation number 4. So if you subtract 4 from equation number 3, you will get m1 m2 m1 m2 common. So you can take m1 m2 into d square del 1 by dt square minus d square del 2 by dt square. So that is equal to ps1 into m2 minus pe1 into m2 minus ps2 into m1 minus pe2 into m1, which can be further simplified as ps1 m2 minus pe1 m2 minus ps2 m1 plus pe2 m1. This can be further simplified as m1 into m2. You can write d square del 1 by dt square minus d square del 2 by dt square as d square by dt square of del 1 minus del 2, that is equal to ps1 into m2 minus pe1 into m2 minus ps2 into m1 plus pe2 into m1. So until and unless we get some relation, we cannot simplify this right hand side term. So let us see what is the relation that we have between the electrical power which is generated from the first generator and the second generator as well. So if you look at this diagram, the two powers are traveling opposite to each other. That means the PE2 value is equal to the minus of the PE1. So now let us consider the same relation, that is PE2 is equal to minus PE1, and try to simplify this equation. So we will have PS1 into M2 minus PE1 into M2 minus PS2 into M1 minus PE1 into M1. So this can be further written as PS1 into M2 minus PS2 into M1 minus PE1. If you take common, this can be written as M1 plus M2. We don't want to carry any mechanical terms with respect to the electrical power. So let us move this term to the left hand side. So then it will become M1 into M2 divided by M1 plus M2 into d square del 1 minus del 2 by dt square is equal to PS1 M2 minus PS2 into M1 divided by M1 plus M2 minus the electrical power. This complete term will be called as the mechanical or the shaft power equivalent. So this is nothing but the electrical power equivalent. This is the equation that we got for M equivalent for incoherent operation of the synchronous generators. We got that M equivalent is equal to M1 M2 divided by M1 plus M2. So, and in terms of the H equivalent, you can write M equivalent is equal to G times of H equivalent divided by pi into F. So, this can be written as H equivalent is equal to M equivalent into pi F divided by G equivalent of the system. So, now we know that the G equivalent is a base MVA of the system. In this, the most important equation is this one. So, if the synchronous machines are not swinging together, then the inertia constant M equivalent is equal to M1 M2 by M1 plus M2. So, if they are swinging together, then the M equivalent value is equal to M1 plus M2. So later if it is represented in the H value, so then substitute and find the equation in terms of the H equivalent for the both the conditions. So this is how we need to find out the inertia constant for the multi-machine systems, that is if several generators are connected in interconnected fashion. So I hope this is clear. Still if you have any doubt, please let me know. Thank you.